So what we're going to do in this quick tutorial is we're just going to look at this beam element example. So you'll have downloaded the CAE file off the Canvas page. So we're simply just going to be looking at the difference effects of the two beam element types. So it'll be a relatively quick analysis today. So first thing is we're going to open up our part. We simply just have a few features here, so it's a sort of a truss thing, but they're going to be made out of beam elements. So the first thing we're going to do is go in and set up our beam properties. So I'm going to go down into my properties module. So the first thing is I'm just going to create my steel material. So we're working in SI units here, so it's going to be 200 GPa, which is 200 e to the 9, and then a Poisson's ratio of 0.3. And then I'm going to have two different cross-section properties. So the first is going to be a I-beam. So I'm going to set up that profile. So I'm going to create that profile. So as I said, it's going to be a I-beam. And we can set up the properties here. So we have here a diagram of the beam that we're going to create. So we have properties L, H, B1, B2, T1, T2, T3, and L is the overall, is the distance from this bottom edge, from the most negative two-direction edge to the centroid, or to the line. Then we have H, which is the overall height, and we have B1 and B2, which are the flange lengths, and then we have the thicknesses of the flanges and of the midsection. So L is so I'm going to say that my overall height is going to be 100 mils. Remember, we're working in SI units, and that my beam sits on the centroid of my beam acts on the center of my line. So that is 0.05. I'll show you the sort of influence of that in a little minute. And then we have B1, so I'm going to say that my they have a width of 50 millimeters, top and bottom, that's 0.05, and then the thickness is going to be 5 millimeters, so that's 0.005 for all of the thicknesses. So that sets up my I-beam. Alright, so I've created that, it's made out of steel, so I can hit OK. Alright, and then I'm going to create another section, but this is going to be a pipe section. So obviously I need to go create a new section, and I'm going to go to pipe, I'm going to call it pipe again for the pipe section, and it's simply going to be a 50 mil radius, so a 2-inch diameter pipe, and it's going to have a thickness again of, we'll call it 0.0, so it's going to be 2 millimeter thick pipe. And because this is less than 1/10 of the rate of the diameter or the radius, I can use a thin-walled formulation. Now, see, when I've done this is one thing I didn't show you in the last analysis. When I've done that, I've added in the new profile, but it hasn't chosen the new profile. It stayed with the original one up the top of the list. So then I just need to go down and change it to pipe, just to make sure I'm using the right cross-section. And so then I can apply the pipe. Then we need to apply these cross-sections. So all of my horizontal members and my vertical members, they're going to be made out of the I-beam. And then all my diagonal members are going to be made out of the pipe section. So I'm going to change that to the I-beam. And then all of my diagonal members, they're going to be made out of the pipe section. As you can see, I have here turned on the render beam profiles on here. So then I can have a look around and I can see that, yep, up here we've been made out of a beam section, and then down here we have our pipe. Now our pipe isn't being rendered, and yours may not be being rendered either because we haven't set up the triads, the beam orientation. So I'm just going to set beam orientation. I want to set it for all of these, and I'm just going to set it so that my N1 direction, so this is going to be my 3 direction, is sort of in the z-axis. So I'm just going to leave it as, which is the outer page direction facing towards us. So I can and just hit enter. Sorry, that's my 1 direction. So that means we have the tangent direction and the 2 direction along the pipes, whereas the tangent direction is along the length of the member, and the 1 and 2 directions are sort of perpendicular. So then we have our pipe section here, and then our I-beam. Now if we go back to our section, and if I go edit my I-beam, so remember here, what I want to do is, because I want to edit the profile, not the thing itself, so I'm going to go edit the I-beam profile. So remember here we had this length offset. If I wanted to move this beam up, I would move it in the 2 direction. So I can just show the, oops, wrong one. I can show the direction of, I can change this length here. So if I change it to 0, for example, you'd see it's moved this beam up. So now the bottom, there is 0 distance between the base and the bottom of my beam. And now if I go edit it again, if I edit that profile again to make it 0.1, it will move that beam downwards. Alright, so you can shift the beam relative to your actual geometry line that you would have developed. But I'm going to set that back now to just be, so it's midway through it, so it's 0.05. And close that off. So that's the effect of that thing there. Alright, and then I'm going to go back into profile view section. Alright, so the next thing I'm going to do is develop my mesh. Alright, so the first thing is we're going to start off with a really coarse mesh, and we're going to use linear beam elements that we've developed in the week 7 lecture, and we're going to look at that. So I'm going to start off with an element size of, I just want to have 1 element per member, so I'm going to set the element size to 8. I'm going to choose my element type. I'm going to use a beam element, but I'm going to use a linear beam element, and then later on we'll go back to using quadratic elements and we can see the difference. And then I'm just going to mesh my part. And so I have 15 elements, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 elements for our system. Right. And as we go through, we're just going to change down the element size in a bit of a verification study. So then I can go down to my assembly and add that in. I'm going to add in a step, my load step, and then, so it's my load step, and then I'm going to add in my boundary condition. So we have 2 boundary conditions that we're going to add in. The first one is this node here is going to be a pin joint, so I'm going to just change the name to the pin joint, and I choose a displacement rotation. I'm going to choose that node, and a pin joint just means obviously it can't translate, but it is allowed to rotate, so there's no restriction on the rotation, but it is allowed to displace in the X and Y. And then secondly, I'm going to have this on a pin roller so that it can move, this node here can move up and down vertically, but it is allowed to, and also it's allowed to rotate, but it can't move in the X direction. So I'm going to create a pin roller joint on that node, and as I said, it is allowed to move in the Y direction, and it is allowed to rotate UR3, but in the X direction it's not allowed to move left or right. And then simply I'm going to apply a load to this node out here as a concentrated force out there, and it's going to be going downwards with a value of 60 kilonewtons. So I'm just going to put negative, and then again it's SI units, so it's negative 60,000. Alright, and that's that load there. So from there we can simply go to our jobs manager, create our job, and submit it. Alright, now obviously we only have 15 elements here, 15 linear beam elements, so it should be relatively quick to solve, which it is. There we go, it's done. And then I want to look at the results. Now obviously this is a very coarse mesh, so I don't expect the most amazing results. And when I go and look at my results, they're not typically interesting. One thing to note is here I have turned off my I've turned off the averaging function, so I've turned off averaging, so I've removed that. And also one thing we need to do obviously is we need to change it so that we're not just looking at one particular location on a beam. So the bottom is the most negative in the to direction, the top is the most positive in the to direction, but I want to be looking at the entirety of the element, so I'm going to go look at the envelope of the element. Alright, so you can see we have a maximum stress of 169.8 megapascals for this system. And the other thing I've done there is I have sorry, I just want to go here. So the other thing I've done here is I've turned on the element numbering scheme. So the way I do that is just go to common options here, and then go to labels, and you can turn on element labels as well as nodes if you want, so you can see which node is which. But I'm just going to choose element labels for the moment, just so I can make clear out my 15 different elements. Alright, then we have a maximum stress, as I said before, of 169.8 megapascals. And now if I go back to my model, and if I go back to my mesh, alright, all I'm going to do is just change the mesh size. So say if we went, if we reduce the mesh size by half, alright, so now we have elements of size 4. I'm going to mesh the part. Now we have 21 elements instead of 15, so it hasn't increased the number of elements significantly. They can go back to the jobs manager. I'm just going to submit that job straight away, just to look at what the change in the results are. Now, there may be questions regarding when do we know our results are accurate. The question is, what level of accuracy over the value of concern is important for you as the engineer? So we've gone from 169.8, so call it 169 megapascals, and now we have a stress of about 175 megapascals. That's a change in 5 megapascals, which may make a change for this system of whether we want to keep this result or not. So the yield stress for sort of a mild steel might be in the order of sort of 250 megapascals, and we're relatively close to that. So a difference of 5 megapascals may mean that we need to continue to reduce down the number of elements in our analysis. Sorry, reduce down the size of the elements, that is, increase the number of elements in our system. So changing from 169 to 175 could be considered a significant change in stress for the purposes of making engineering decisions. If the change was maybe 0.2 megapascals, then potentially that doesn't change my engineering assessment of the system. So we can go back down and we can go back to our mesh, and we can change the mesh size down. We might change it to 2 meters, and then we can mesh our system again. Now we have 49 elements, and I will submit that job, and then we'll be able to look at the results for that. So when I've increased from 21 elements to 49 elements, that's a roughly doubling of the elements, which means that the actual solving time of this, the time it's spent solving it, not just inputting the data or getting the data out, increases roughly by a factor of 4. It's about 3.2, but yeah, so roughly if you double the number of elements, it takes 4 times as long to solve, as a rough rule of thumb. So we can look at our results now. So we've gone from 175 megapascals to now 178. So again, this is still a change of 3 megapascals, which is getting small, but still may be enough for me to make engineering decisions. Now, what we will note is that the profile of the stress has changed. All right, so here we can see in the middle of this section, for example, that we've gone from this element 41, we have a maximum stress of 164 megapascals, and then in this middle element it's dropped down slightly to about 162 megapascals. So that is a change which we weren't able to resolve previously with the smaller element, the larger element size. So then we can again drop down the element size. We might drop down to 1. We can submit our job again. Whoops, I didn't. I changed. I need to remesh it. I forgot to remesh it. Yes. So now we have 89 elements. Go to Job Manager and submit that. With our 89 elements, that's successfully completed. And now we can look at the results of that. So now we have a lot more elements over our system. And when we look at the stress for that, we've got roughly 180 megapascals. So again, another change of 2 megapascals. So it's slightly increasing every time we increase it. Now if we drop down the size again, now to say we'll change it down to 0.2, and we will mesh our part. Right now we have 445, so this is a very large increase of the number of elements. So previously we had 180 megapascals. And now we'll see what the change is. Now, one thing to note is that we as operators sitting here in front of the computer, we don't really notice a change in the time duration taken to solve the system. So in an engineering office, you wouldn't really be too concerned about the fact that it's taken very slightly longer to solve it. But what you still want to know is that your study is independent of the number of elements. You want to be able to have confidence over your model. So now we've changed to a system where we've gone from, I think it was 179.8 megapascals to now 180.9. So it's a change of about 1.1 megapascals. So this is now starting to get to a point where the results aren't really being changed by the element size. All right, and this is for a linear element. So we've got now a stress of 180, we'll call it 181 megapascals, 180.9 megapascals. Now what may happen if I go back to my mesh, and rather than using linear beam elements, what happens if I change to quadratic beam elements? Now quadratic beam elements obviously have a mid-span node, so that's where it says here a 3-noded quadratic beam element on a plane. All right. What we'll do is we'll change back to an element size of 8. All right, and then we'll remesh it. So now we're back down to 15 elements. And we can submit that job. Now each of those, even though we've gone down to 15 elements, each of those individual elements now takes longer to solve because remember, with a 2-noded element for a beam element in plane, you're looking at each node has 3 degrees of freedom, and you've only got 2 of them. You've got 2 nodes, so you have 6 degrees of freedom, so each stiffness matrix is 6 by 6. But for a quadratic beam element, that's a 9 by 9 matrix, so even though you only have 15 elements still, the actual computational cost is slightly increased. But now let's look at the results. All right, and now the stress is immediately back to what we were looking at before. So we're looking at 181.1 megapascals, so that's a difference of 0.2 megapascals between the 445 elements for linear beam elements versus the 15 elements for a quadratic formulation. Now we might want to see what happens when we still need to demonstrate that the result is independent of the number of elements. So we might change that down to 4 mesh size, and we might remesh it. Now we have 21 elements, and again we could go into our jobs manager and submit that. And again, it doesn't take particularly long to solve. And we can look at our results. And now that maximum stress hasn't changed at all. So essentially, what you'll generally find is that the stress reduces greatly. We have much more mesh independency with a lot fewer elements when we use quadratic elements as opposed to linear elements. So this is why we always recommend that you use quadratic beam elements as opposed to linear beam elements. Alright, so that's the tutorial for today. Good luck with the assignment, and I'll catch you.